Good morning to all of you. This is Professor Nijjhat Dhang again on the third session from IIT Kharagpur. So we would like to make today that multi-storied frame and one emphasis on the earthquake resistant structures. So we are not going up to construction, but anyway, just planning that how shall we do it. Let me show you. Before we start, uh, so this is one multi-story frame, 100-story building, which is due to earthquake. This is vibrating. You can see this one that vibrating for El Centro earthquake. This is a particular model. You can see how it is working. Okay, I hope you can see this view that 100-story frames where in each floor that is actually lumped mass and it is vibrating due to earthquake. That earthquake hits on the foundation and you can see that how it vibrates and finally it will come to the end. And here we would like to find out that how much actually maximum lateral displacement allowed, that we have to see first. That is number one. And number two, that between two floors how much maximum is permitted, that is called drift. So how much maximum lateral displacement permitted between two floors, between two successive floors, and also the overall displacement. You can see at the top that displacement, lateral displacement is more compared to the ground floor. And this is a particular earthquake, that is El Centro earthquake 1940. So now let us come back to the one just to give you initial demonstration, because we need we have to show it in a different way. So now let us come back to that just quickly, that earthquake. Before that, let me show you certain cycle. This is called disaster mitigation cycle. That means it may be earthquake, it may be cyclone, tsunami, fire, many more such things are available, that which we call it actually disaster. And when the event starts, and when this event starts, this one, then immediately we need certain time, that is called emergency. That may be few minutes to few hours, and then we go for recovery. This is one part. That means when disaster happened, then immediately you have to go emergency, that one, that urgency, other things, and then recovery. Finally, this cycle we are having, we are monitoring that prevention, mitigation, and preparedness. So we are going to this cycle here like this. This is the called actually disaster mitigation cycle, and it is true for earthquake also. Now, how do we know that this is the whole world where we are having those, say, these red points? That is the point where that earthquake occurred. So whenever that particular one, say, earthquake occurred, this particular one, and it shows that are the actually the boundaries of different tectonic plates, boundaries of different tectonic plates. That is the one you could find out here. Next one. So on the basis of that, the tectonic plate, where we are, all those things actually can be given, and that one, the different kind of tectonic plates that you can find out, and it moves, and because of that, that earthquake occurs. You can see this one, the different position here, like lithosphere and crust. I have taken these photographs from the internet, and this is just for information. And lithosphere, then so only this portion where we are having that actually problem that occurs here, that we are not interested here, the liquid, solid, other things, but only here wherever we have, because of that earthquake occurs, and that we have to find out. Now the thing is that when earthquake occurs, there is one wave that is called P wave. P wave means that it will be compression, then like this, all those things. S wave means something you can say wavy, you can consider, and it has a separate wavelength and amplitude. So this is your P wave and this is your S wave. Both waves actually generated at the time of your earthquake, and it travels. This is the one you can consider, this one as a seismograph. That generally the one if it vibrates or oscillates, on the basis of you can find out the earthquake. Now one popular one you have already heard, that is actually Richter scale. So in Richter scale, we are having this one, the time, That means here S wave and P wave. Now one thing I would like to show you, P wave obviously it is straight, so it will reach first. S wave, that wavy, so it will reach next. Out of these two waves, though they are developed at the same time, but P wave will come first and S wave will next. That means here that if there is a oscillation, there is a say pendulum, so that one will start vibrating when the P wave will come, and it has a amplitude very less, but when S wave will join, then it will vibrate more, that amplitude will be more. So we can find out this time, how much actually time, the gap, that we can find out. That means if we can find out the time, so immediately we can find out the corresponding distance also. So whenever we can get that one, we can get the distance also, and I have another side amplitude. So one side I have time or distance, another side we have amplitude. Both of them when you join, then I shall get the magnitude in Richter scale. So this is the one we can get it. That means anywhere that earthquake occurs, what I can find out from the difference from P wave and S wave, we could find out that how far it is. That means you are standing in a particular point, you are sitting. So if you can get this P wave and S wave and the difference of that, you can find out of a certain radius that earthquake occurred, but you don't know where, but it has occurred at a certain radius, the circumference of a circle. So that way you can say, now this is your another one, we can consider that one, that what are the different cases of earthquake, all those things at different position. We can find out distance, and the circle means what is the magnitude. That is the one. I have taken it from USGS. So as I have told you, so the earthquake occurred at a particular point. So there is one seismograph here, there is another seismograph here, there is another seismograph here. So if we have three seismographs, so you will get one time on the basis of you will make one circle. Okay, that means it is anywhere in the within the circumference of the circle. You will get within this one. So wherever it will meet, at 2 points it will meet, that means either it can be here or it can be here. Now when you have third seismograph, then obviously I can say this earthquake that is here somewhere here. So that means a single point. That means I can find out that one, that the location of the epicenter. So that means we need three seismographs or three seismograph station from where we can find out where that earthquake occurred. This is the earthquake we are having, the great earthquake, major, strong, moderate, light, minor, and then 8 and higher, maybe annually 1, 7 to 7.9, maybe 18, strong 6 to 6.9, 120, moderate 5 to 5.9, 120, light 4 to 4.9, 6,200 estimated, minor 3 to 3.9, 49,000, very minor less than 3. So you can consider this one say 1,000 per day and 8,000 per day, like that you can consider. And this is the one modified Mercalli intensity 1 to 12, insignificant, very light, light, moderate, slightly strong, strong, very strong, destructive, ruinous, then disastrous, disastrous in extreme, and catastrophic. So we can find out all of them, only detected by instruments, only felt by sensitive persons, small vibratory motion, felt inside buildings, felt by most persons, damage to non-seismic resistant structures, people running, some damages in seismic structure, serious damage to structures in general, serious damage to well-built structures, only seismic resistant structures remain standing, general panic, almost total catastrophe. And the corresponding Richter scale, this is 1 to 1.9, 2 to 2.9, 3 to 3.9. So we are more interested in the 5 to 5.9, 6 to 6.9, then 7 to 9, to 8 to 8 to 9. So that means here we can find out a relation between the modified Mercalli intensity and the. This is very interesting thing I would like to show. This one, that Andaman Sumatra, that tsunami, so it occurred here, and that is actually felt by different seismographs all over the world situation. What we have done, so if this is the location, then we have arranged it that how close this one, in the one that's closest to one first, and farthest one last, because this particular one, so obviously you can consider farthest one like the different seismograph. So that way you can, that means first obviously whoever here he will feel first, then he will feel like that, he will, all of them will feel actually that way. So if that be the case, now the earthquake occurred, so the P wave and S wave moving this direction also as well as this direction, because it will move also in east to west direction as well as east to west, and this side also it will move. That means this side also move and this side also will move. So if that be the case, what happens, let us see. So that means this is the one which is going like this, this is the one which is going in that purpose. That means same time one started like this, another one started like that. Means he will first feel that earthquake, seismograph, what is the seismograph station. So he will first this one, then he will find this one. Similarly, after one round also, if that is a very high one, then also you can feel. And this way it is going after one round, this also it can feel. That means if it is say your phi or certain time t, and then it will be say another side, this one will be 360 degree plus 360 degree plus or 2 pi plus. This is again 2 pi plus in this direction. So if that be the case, so we'd like to find out that how strong that earthquake. So if you see this one, this is the earthquake that first time they are getting this one, then second one, then say third one also there, then fourth one. That means you see that earthquake was so strong that even first time you can observe, you can feel, even after rounding one more, then also you can feel that earthquake. So it was so strong that even then also there is some kind of thing is there. That's why I'm telling you here. That means not only you have seen it first, but also after one round also you can see. Not only you have seen next one like this, but after one round also you can see. That's why we are getting here 4. This is first one, closest one. This is second one, the other way it is coming. This is this one after one revolution, and this one is after one revolution. This is the first revolution, this is the second revolution, like that. So you can imagine how strong the earthquake was. Now I would like to say that related to structures, what happens actually. With related to structures, that one we are having actually here, that is called actually mode shape. As you can see that it is very easy. Let us say that one stick is just only your that hold it on the ground, and with one hand you can simply pull it and the shape will come like this. Let us say you are using two hands. One hand you are pushing this way, another hand you are pulling this way. That means you are pushing this hand and you are pulling, then the shape will like that. Here I can say you are using only one hand, by that you can do it, but here you require two hands. But here what about this? This one to be more surprising, that means you are using one hand here pulling, this is another hand you are pushing, or this one say you are pulling, this one you are pushing, and you are using your say one leg which you are pushing this way. That means you are pushing this one to get this one, then you are pulling this one, and then you are pushing. That means in this case one hand is sufficient, in this case you require two hands, in this case not only you require two hands as well as you require your leg. That means here one limb is sufficient, here you require two limbs, and here you require three limbs. That means otherwise I can say here you require less energy, compared to this you require more energy here, compared to this you require further more that energy here. So that means to get the different mode shape you require different energy. This is called first mode shape, this is called second mode shape, and this is called third mode shape. This is called actually accelerometer, that by which you can measure the acceleration, and you can get this information in detail in structural dynamics course. This is called accelerometer, that modern accelerometer, that one actually made of piezoelectric, other things that they make it. So you can see that how it has become so small. Now what happens here, that whenever you are having response for a particular time period, then you are having certain amplitude here. Then you are having this 0.5 second, this is 1 second, this is 0.2 second. This one I have taken from Chopra book on structural dynamics. Now this particular one if we have, then I can find out that different type of amplitude, different amplitude we shall get. Now let me give you one example. Let us say consider one glass of water. Let us take a steel glass, and on that steel glass that you have filled up with the full water that you have filled up, and let us take a spoon. Now if you strike the edge of the glass, you will find out that water is coming out. Similarly, water will go out of it. But if you just simply keep on heating, and if you hit more and more, you will find out that water is not coming out. That means that amplitude will be less. In the first case, just you have struck once, and that is called impact. Because of that, water has gone out. If you increase the frequency of that one striking the glass of water, and that full glass of water, you will find out that water is not coming out. That means with the high frequency more, amplitude will be less. So this way we can find that means time period is less, means frequency is more. 1 by t is the frequency. Here 2 seconds, that's why you are getting more amplitude. This is your call actually that response vector for L centro ground motion that we can find out here. And this is the one actually here you can find out with different type of actually vibration period. You can find out different type of, you are getting the different actually response, you are getting that particular one here. So this is the one actually we are interested to know that how shall we design the structure. So coming to that one here for our case, that is the one just to give you an introduction on earthquake, how it works, all those things. Now let me come back to that actual code which we follow. Already I have told the front page, that is your say criteria for earthquake resistant design of structures. So this is the general provisions and building. There are so many parts, but let us just quickly go through this one, how it comes. So there are so many things are there, but only thing I can say, part 1, general provisions and buildings, liquid retaining tanks, bridges and retaining walls, industrial structures including stack-like structures, dams and embankments. There will be 5 parts. Actually, we are having part 1 and part 4 only right now that is released. But I am not going to detail about it. Only thing I like to show you that one. You are familiar with this one. So this is the one that earthquake zone. So you are having right now there are 4 zones because zone 1 is merged to zone 2. So zone 2, zone 3, zone 4 and zone 5. This one you see that zone 5, this one also zone 5. Here also you will find out that certain pockets are there zone 5. Then these are the major one we are having zone 2, and this one we are having zone 3, and then remaining one like that we are having here zone 4. So these are the 4 zones. Earlier you had 5 zones, but now zone 1 and zone 2 that is merged, and we have 4 zones, and for each zone we have to find out the characteristics, and that one we shall get it from this code. Let us come back to that. We are not going to all those things. Only thing I would like to say here that as you can see, we shall come back here when we shall do the multi-story frame design. There we can find out that is a 1.5. This is dead load and imposed load. 1.2 dead load plus imposed load plus minus earthquake load. Either you have to add that one, so that means here it is 1.5 times and here it is 1.2 times, and then it will be plus and it will be minus. It will be again 1.5 times dead load plus minus earthquake. No load is taken for the live load. 0.9 dead load plus minus 1.5 earthquake load. That means you are reducing the dead load here and you are increasing the earthquake load. So 0.9 dead load plus minus 1.5 earthquake load. So this is the one, the different factors we use it for different load, all those things we consider. Now coming to this one here, what we would like to find out, that this is the part that we would like to take it. This is called actually one factor, the Z I 2 R SA by G, like that. So this is the one zone factor. We have actually 4 zones. So what are the value, first parameter, what is the value that we have to find out. So these are the one zone factor Z. For 2, Z will be 0.1. For 3, Z will be 0.16. For 4, Z will be 0.24. For 5, Z will be 0.36. So first part, that is over. So I can get the value of Z. Next part we have I. Next part we have I. What is I? I means importance factor. So how the building is important, say for example any assembly building, any heritage buildings, so that important buildings, that one we can importance factor depending upon the functional use of the structures, characterized by hierarchical consequences of its failure, post earthquake functional needs, historical value or economic importance. So this one we shall get it here, that your importance factor. So the value we shall get it our importance factor. So we can find out that one. So what we can do here, that importance factor, that we can get it from table 6. So please note down that table 6, either it can be 1.5 or 1. So now we know Z. Now we know Z. I know I. Let us about see that below. What about R? So what about R? Let us find out that particular one we are interested. And then, so this is the one, that value of R. For different kind of structures that R, that we can find out ordinary RC moment resisting frame. So 3, special RC moment resisting, so 5. So like that we can have different values that I can find out from this one. That is also we can get it from table 7. So from table 7 we can get that R. Now we would like to find out here the next term, that is SA by G. So Z means depending on the earthquake zone, I means the structure, whether you are getting 1 or 1.5, R means moment resisting frame. From there you can get the value, maybe 3, maybe 4, maybe 5, and so like that. And then next part we have SA by G. So SA by G is the next term. So you can find out that SA by G here. As you can see, the structure already we have done it. So this is called actually SA by G. So for different value, if it is type 1 soft, medium and soft soil, so we can find out the different curves. This is the one curve. From there, what I can find out, we can find out the SA by G from the, that means if I know the time period, then from there I can find out the value SA by G, that we can find out here. This is the one, that curve we can find out. So that means here we have to find out Z I R, like that we have to find out. The next thing is coming into picture, just to one term, that horizontal force VH equal to HW and TH equal to 0.09 H by root D, actually it will be. So from there I can find out the time T. So I can find out from the time T, and we can find out and we can calculate that. So what I'd like to do it here, just to give you idea. First thing we have H will be equal to Z by 2 I by R. So Z by 2 I by R into SA by G. So this is the one we are getting here, H equal to Z by 2 into I by R into SA by G. So I am getting this one. So Z from different zones, I importance factor, then R resisting frame factor, and then SA by G, that we are getting from soil condition. So that means I can get this value H. So I can get the value H that we can find out here. Then what we shall do, that VB will be equal to AH into W. W means vertical wall, vertical load or gravity load. So we can find out this one here, and then we can find out say QI, VB, WI HI square divided by summation WI HI square. So this is the one that QI we shall get, this particular value QI we shall get it from the, that is our objective here. So that means, just to summarize the whole thing, what I would like to say, we shall use IS 1893 part 1, we shall use IS 1893 part 1, from where we shall get that H equal to Z by 2 into I by R into SA by G, and from where Z I shall get the value if it is in zone 2, because that where you are going to construct that building, that we should know. So from there we can find out it is whether it is in zone 2, zone 3, zone 4, zone 5. From there we can get the value of Z, and then after that we shall also find out I. Most of the cases I equal to 1, because that is not a special set of structures. So I equal to 1. R generally it comes 3, 4 or 5, that it all depends. So that means here, if R is less 3, then AH will be more. If R is 4, AH will be whatever the value, it will be further. So if it is 1/3, 1/4, 1/5 of these value we can consider. So that R you can SA by G we shall get that particular one, that curve we can find out. So if I can H, and we shall calculate W, so I can find out VB, and this VB, the base shear, we call it say base shear. This one we have to distribute along the floor. That means here we have this structure, say this is one, this is another one, this is another one, and then if I consider this one say your H1, this one say your H2, and this one say H3, and let us say this is W1, this is W2, this is W3. So I can find out W1 H1 square plus W2 H2 square plus W3 H3 square. This is nothing but summation of WI HI square. This is the one summation. This one, that means W1 H1 square plus W2 H2 square. So this one. So if it is in the first floor, W1 H1 square divided by sigma WI HI square. Similarly, W2 H2 square for the second one, and third one, like that we can find out. And that is the corresponding one, I can say this one, this one, this one, Q1, Q2 and your Q3. So Q1, Q2 and your Q3. So that way we can find out the value. That means due to vertical load in a particular zone, I know that condition of the soil, importance factor, how the resisting frame. If I know, then I can find out H, and knowing that one I have to find out the lateral load. That means earthquake load, that one you will have here, that lateral load that you will have. So that is the thing actually we shall find out here, that our objective here to find out that value. So what we can do it here then. So this is our objective here. We have to find out QI equal to VB WI HI square divided by this particular one here. VB equal to H into W. We can calculate W. AH we can find out the formula, and we can find out the time period T. If I know the time period T, so from here we can find out from this curve we can find out What is the problem is, if I know the time period, immediately I can find out what is the SA by G, this SA by G coefficient, how much it is, that we can find out. And on the basis of that, we can calculate that alpha H or AH and then VB and then Q at different points. So this is the one we generally do it for the calculation. So now let us come back here, because this is the basic thing we do it. That means here we are having dead load and then we are having imposed load, and due to that we have to find out the vertical load, and from there we can find out that what is the effect laterally, how much lateral load you will consider, that is your say earthquake load. Now let us come back here, the problem. So now let us come back that one simple problem, that one whatever we have done in the last class. So next problem, let me go through it quickly, because we have already discussed this problem yesterday. Our next problem, we have to find out that floor to floor height, a simple problem. Floor to floor height of a G+2 storied building is 4 meter. The weight of each floor is 300 kilonewton. Weight of each floor, that is 300 kilonewton. The weight of roof may be taken as 250 kilonewton. Center to center distance between outer columns is 12 meter. Calculate the lateral force in each floor developed due to earthquake. Take earthquake zone as zone 4, soil condition medium, importance factor 1, and moment resisting frame factor as 4. So if you take, this is the problem, I repeat once more, the floor to floor height of a G+2 storied building is 4 meter. So G+2 means ground plus 2 more floors. So you have first floor, then you have second floor, and then you have the roof. So first floor, weight of the first floor, considering say your dead load, self weight, and then superimposed load, that is 300 kilonewton. Second floor also same value, but for roof you may take 250 kilonewton because live load may be less. The center distance between two outer columns are there, that is the 12 meter. So calculate the lateral force. So you have to calculate the lateral force for earthquake loading, where earthquake zone is considered as zone 4. Soil condition you have considered medium, importance factor 1, and moment resisting frame factor as 4. If we take this one, and we have very simple calculation, earthquake zone 4, earthquake zone for that value 0.24, importance factor 1, moment resisting factor 4, height of building H, because we have considered here earthquake zone 4, earthquake zone this one 0.24, importance factor 1, moment resisting factor 4, height of building H 12 meter, width of the building I have already told 12 meter. I should not give the same value just for distinction. Anyway, this value 12. So time period 0.09 H by root over D. So I am getting here this value 0.312 second. If I know the soil type medium, SA by G equal to 0.25, earthquake coefficient alpha H or AH, that is in the code, Z by 2, I by R, SA by G 0.075, base shear VB equal to alpha H into W, because we are considering here 600 plus 250. First floor 300 kilonewton, second floor 300 kilonewton, and then roof 250. So total 850. So that means total base shear is horizontal base shear, that way you can consider, that is actually here you are having 63.75 kilonewton. So if we consider that, then I have written here 300, 250, height 4 meter, 8 meter, 12 meter. So this one I have calculated, total you have calculated, then I can get this value here. Please note this value should be equal to 1, 0.08, 0.32, 0.6. So I am getting here 5.1, 20.4 and 38.5. So this is the one, that calculation which you have to calculate from earthquake coefficient or seismic coefficient method. We have not got the other one, but anyway this is a good one you can consider for a starting one, because in design of RC structures this particular method you can use it. So, I can find out that if there is 850 kilonewton load distributed on the building floor wise, in the first floor 300 kilonewton, in the second floor another 300 kilonewton, and at the roof 250 kilonewton, then for earthquake zone 4, importance factor 1, moment resistance frame factor 4, the and soil condition medium, we shall get the lateral load, that horizontal force you can consider 5.1, 20.4 and 38.5 kilonewton. So, I would like to say here like this, what we have done basically, okay. So, what we can do it here, that means I am having this structure, this is vertically downward W1 300 kilonewton, W2 again another 300 kilonewton, and W3 250 kilonewton. So, W equal to W1 plus W2 plus W3, which comes as 300 plus 300 plus 250 equal to 850 kilonewton. So, if that be the case, so I am interested to find out what is the value of Q1, what is the value of Q2 and what is the value of Q3. As you can see that in the very beginning I have shown you that video where it is moving laterally. So, when it is moving laterally, then we have to find out, that means obviously there is a horizontal force, and that force how it is distributed, that force distributed Q1, Q2 and your Q3. So, that is the one we find out, that we can see actually here. So, that way I can find out here. So, 5.1, 20.4 and 38.25. So, that particular force we have to calculate and we have to find out here. So, this is the one we calculate one, and now let me show you once more. Let us go back to that IS 1893. So, then it will be clear again that where from I have taken those things. So, this particular one here, what we are doing basically, first thing you are finding that from the location where you are actually, and on the basis of that you will find out that which zone, whether you are in zone 2, zone 3, zone 4, like that. Then what you will do, then I shall come back to the codal formation, because I have to find out the age. So, I have to find out the value of Z. So, it is dependent on the Z. So, from this table 2 you will get the value of Z. If it is zone 4, it is 0.24. Then you will find out that your time period, and on the basis of the time period you can find out from here or from the equation given here, and knowing the soil condition, if it is medium soil condition, then if it is say time period is less than 0.1, then I shall use this formula. If it is greater than 0.1 and less than 0.5, then I shall use this one constant. If it is greater than this particular one here 0.55 to this one 4, then I shall use 1 by 1.36 by T. So, this is the one we shall use that particular formula to find out the that age. And when you know the age, so when you know age, you can find out that base year also, and after getting base year I can distribute along the floor what will be the corresponding load along the floor, the lateral load. So, this is the one we are doing. So, that means in the first few pages you will get all the information regarding that earthquake load. That means if I can calculate earthquake load, then I can analyze the structures due to dead load, due to live load, and then lateral load. So, I can find out, and on the basis of that we can compute the bending moment shear force in each member. So, this is the one that we would like to do it for the earthquake, and which already I have shown that one here, So once more, let me go back. A simple problem which we have done it, and this problem we have done it, and then we have calculated that. So issue, there are certain things are there, that why are you considering that one as a lumped? The first question, that one we are considering, this is made of beams, other things, all those things. Let me just come back here, then it will be clear to you. Let me just simply come back and show you. Now just let me show you that one frame so that you can get an idea. This is just a model I have considered, a building frame, and this particular one developed by me only. And yes, there is a question here, say type of foundation which we provide can affect the design of earthquake resistance structures. So type of foundation which we provide, definitely that particular one also there. Let us consider for the time being, we are considering here isolated footing. Mainly we can consider that one, say isolated footing. Just to give you idea, different kind of, because we are only considering here in this case the three types. Just to give you for your information, just let us go back to that 1893, and then it will be clear to you, which I thought I have explained. But anyway, so this one, let me just come back to you, that again the same thing, that where I am getting that so far what information we have actually, then on the basis of that we shall decide. So our objective here, that so far the information we can say that this is the one that we know. That means here type 1 rock or hard soil, type 2 medium soil, type 3 soft soil. So from here there is no problem, but after that, with the period more, then we can get that one three different curves, one for the hard soil, another for the medium soil, another for the soft soil. That is the one we are getting, and generally we get that particular one, say bearing capacity, other things we get from the geotechnical investigator. After investigating the soil, they provided the safe bearing capacity. For that time being we consider, but since I would like to make it here, there is further, it is possible actually, just for your information, there are actually three different categories of interaction. One interaction, that is called actually soil structure interaction, or we call it SSI, soil structure interaction. FSI, and just to give another one, that is called, just to complete that interaction, vehicle bridge interaction, which is called VBI. Now soil structure interaction means, if you go further the study, particularly say for example you are having column, that piles, different type of footing, as you have rightly pointed out, those things actually you can study, and that is, you can consider that one in a advanced stage. But whereas fluid structure interaction, if you consider, that is also with respect to building, different wind, other things that we comes, also for bridges also it come. Just for your information, I would like to tell you, possibly you have read that one in any physics book. That is actually one bridge called Tacoma Narrow Bridge, long back in 1940, 1940, that bridge collapsed within 6 months from the date of commissioning. The bridge when constructed within 6 months, and that was because of actually aerodynamic effect. The aerodynamic effect of the bridge was not considered that time, it was not known to us, and that's why there was a catastrophic failure. There is a video also, if you see that one, there video available also there. Anyway, so similarly this is also part of fluid structure. This is true for building also, building and wind, that is also there. And vehicle bridge interaction means actually further one like to go, that for bridge that so many vehicles are passing, moving, and on the basis of that also you can find out that interaction. This is called actual interaction problem, that way you can find out that. But for the time being we consider this way only, we consider. So coming to this one, so that means we are interested here that type of soil, from there we can find out that. Now let us come back here again, the problem which we have started, that is our objective, the multi-story frame. This is one, say, building, let us consider. So it does not look good that it is actually obstructed with this deck slab, other things we can consider. This is the footing, let us say I have considered footing. Then you are having up to plinth level, it is clear now. At the plinth level, that particular one you are having columns, you are having up to certain level. I have just give a distinction of this one of different color of columns, so that it will be distinguishable from the beams. Further, there is another view, this is other view. We are okay, I shall come back to you this question later on that ORF and SRMF. Anyway, let us complete that session first. You can see this one, that where from you are getting the value of R, response reduction factor R for building systems, ordinary RC moment resistant frame, that means the building whatever you are considering that one, OMRF, so that is 3. Special RC moment resisting frame, that means you have given proper development length, that joints, that one actually properly it is actually resisting moment, and that you can consider this one as a 5. So this is the one you can find out here. Ordinary shear wall with OMRF, ordinary shear wall with SMRF. So different values again we are getting. Ductile shear wall with OMRF 4.5, ductile shear wall with SMRF 5. So what does it mean? That you can see this one, the value you are getting, the value less than 3 to 5. All the values whatever you can get it here, that in this case of course that we are getting load bearing wall, all those 1.5 other things. Otherwise the values you are getting here between 3 and 5. So R for this case, this is between 3 to 5. Sorry, I think this one I have to make it. So I am getting here 3 to 5. R equal to I am getting 3 to 5. So H equal to Z by 2 I by R SA by G. Let us take out here like this, H equal to 1 by R Z by 2 into I into SA by G. This is one parameter. Now I am getting here 1 by R. So that means this is one parameter. So let us consider this one as a C. So H equal to 1 by 3 C, H equal to 1 by 4 C, AH equal to 1 by 5 C. So this means 0.33 C, 0.25 C, 0.2 C. That means this parameter are going to change with respect to the different value of moment resistance. That means here that if the ordinary, then we are getting 3. That means this AH will be more. Whereas if I consider the special resisting frame, it will be 5. So this one will be again AH less. So that means how we are constructing that one, on the basis of that, how the joints are there, whether how far that is moment resisting, whether the proper development lengths on the steel are given. On the basis of that, you can decide that whether you will go for 3. If you are conservative, that means say no, whatever it is they have done, you do not have any trust, you do not actually have any confidence on the construction, and then on the basis of that, what you can do, you can take 1/3, that means R equal to 3. But if you see no, it is a good quality of work, they have given proper development length, and it is really the one is resisting the memory resisting frame. So I can consider this one as 5. That means I can consider that your lateral load will be less. Here in this case lateral load will be more, in this case the lateral load will be less, less, and this is more. So that way we can find out that value. So this is the one, that frame. Now question is here, how shall we design this? This is our next thing we would like to find out, that how are you going to design a multi-storied frame? How are you going to design a multi-storied frame? So let us take, though I have taken a, almost similar problem that I would like to show you. What we shall do it here, that frame which you are considering here, let me, I shall not be able to hear your answer. Let me ask you a one simple question, that is the starting point, and you think yourself and you and then we would like to find out first. Let us consider of our design of multi-story frame. Now the thing is that we are having certain length here, and we are having certain width here. My question here, I have rectangular columns, just to give you like this, rectangular columns. So this is your rectangular columns. Let us consider this one as 300 by 500. This is 500, this is 300. My question to all of you, how shall I provide the column? Shall I provide the column like this? I mean to say, shall I provide the column like this? That means here rectangular this way I am having, or shall I provide this way? Which one is preferable? Or we can do any one of them. I have a rectangular column, say if you have a square column, then there is no problem, and you are more lucky if it is a circular column. So life is very easy. So, but as I have told you yesterday also, that life is not so easy and it is really complex. So you have to find out the solution. So in this case, my question here, that if I have a rectangular column of 300 into 500, this side it is more, this side it is less. So shall we provide this way or shall we provide this way? Anyone, these are the two options. I am not considering any other inclined. I am only considering two options 90 degree. One can be in this manner or it can be in this manner also. So anyway, so let me respond to this particular one here. Okay, so there is one question here, what type of prevention techniques is adopted for underground structures in zone 2? Okay, so I think this one will take some other one which it may require another time actually, that anyway. So there is certain kind of things actually that you have to design it. Say for example, one way you can consider water tank also, that, or say swimming pool, that also you can find out. Some other structures also you can find out, and where that you are loading other things you will consider. What I can suggest actually, let us concentrate on the multi-story frame, and from there itself you will be able to understand that what type of that your technique you have to use. So let us go step by step, and then you from there with our discussion you will be able to know that what type of prevention will get it. So okay, so I mean to say, if you are so this is your number 1, this is your number 2. I hope you are telling this one as 1 and this one as 2. So I have got one. Thank you very much. I have got one answer, that first type of column, that is actually preferable. So why? Because you see the building. If we now come back to that particular one, just let us consider the building, then it will be clear to you that one. Just please bear with me. Yes, if we consider this one, it is very easy to bend from this direction, whereas it is very difficult to bend in the other direction. That means if we consider this structure, here, this particular one, this direction, that means I can bend easily from this way. If I push this one, then I can bend easily. And maybe it is true for earthquake, it is true for wind also. But if you like to push this one, it is very difficult to bend. So that's why the weaker, actually we should always help the weaker one side. We should be always on the weaker side. So if you are in the weaker side, that's why we prefer this type of, we prefer number 1 and not the number 2. If you use this one, then obviously it will be uneconomic. It will be uneconomic. It will not be economic one. So that's why we prefer this particular one here. Now let us come back here, our another problem, that so we can get this type of problem. Now the question is here, how far it is correct we shall use only one frame. How far it is correct that we shall use? So that means this particular frame, how far it is correct that we shall use this side of frame, only one frame, or shall we go for 3-dimensional? Shall we consider slab in our analysis? We do not consider in our analysis, we only consider frames, that means beams and columns. Only loading on the slab we consider for our analysis, but we do not consider in our structure analysis, that we do not consider the strength consideration of the slab. Wall also we do not consider, we only consider that one, say, self weight of the wall weight we consider here. So first starting point here, what we do actually, we design 2-dimensional frame, and that is good enough. And you can, I can tell you right now, nowadays you are doing 3-dimensional other things, that is all right, but also you imagine that so many buildings are constructed and still they are standing based on the 2-dimensional analysis only. It is done on the basis of 2-dimensional analysis, and then it is, there are so many buildings, so many that one. So that way you can see that particular one method. So however, you can compare your results with any commercial software, you can compare and you can find out that. So our objective is that now we shall come to the last part of our thing, that is your say that multi-story frame, that which already I have circulated, and let us see this one here, and that one I have just made in that particular format. So let us come to this. So let us come back to that, and I have already discussed, already I have circulated. So let us, I hope that, yes, there is one more question, that could you tell me what is the new trend available to prevent our structure from earthquake? Okay. This is a little bit one way you can consider that one, say there are two aspects. One aspect, that one we are considering from the structural design point of view, and that is the main objective of these few lectures whatever I am giving for last 2 days, also today the concluding session that I am giving you. So we have to think of it from the structural point of view. So if we consider that one from the structural design point of view, so your detailing, that you would say ductile detailing, other things that also you have to consider in our structures, that we have to consider. We shall come at the end, certain portion we shall come, but before that we shall, let me complete this one, and then now just to quickly let me tell you that particular one here. Say for example, that after Bhuj earthquake, the hospital built at Bhuj where they are having actually bearing at the foundation. Generally, we do not provide any bearing on the foundation in a building, but there they have given that bearing at the foundation level, because so that they can resist earthquake, that particular one, and they can do it actually that you will say foundation system and with the structure they are separating that, and that is one is possible. That is number one. Number two, nowadays there is a trend that is called actually structural control. So structural control is another. Say for example, one high-rise building say made, and that one it happens actually, say for example, at the top floor the residents who are there, they are feeling discomfort because of the lateral movement of that. So obviously that such a high-rise structures is made, and you cannot actually that demolish it again reconstruct it, because that is not actually possible. So that's why the another new technique has come up, that is structural control, and using that actually they would like to, they always actually reduce the vibration, the lateral vibration. So there are two aspects. One is that one you try to make it at the design level. Otherwise, when it is already with considering all aspect of design, other things, even then also the lateral vibration is more, then you control with the structural control mechanism. The tuned mass damper, tuned liquid column damper, like that so many things are available nowadays they are doing, and on the basis of that do it. But that is a separate issue, but mainly let us consider on the, this is the on the structural design part only. Now coming to this one here, already I have given you these things. So just to quickly give you that idea. So this is the problem. This is the plan of the building. This side it is say 5,000, 3,000, and again we are having say 5,000. This is all we are having 4 meter each. What we will do then first? What we will do? So I shall do first the slab design. Already I have shown you that one yesterday last, the slab design. So what we will do that already now you know that how to design the slab. So that means this is two adjacent edges discontinuous. One, this is 4 meter side, so one short edge discontinuous. This is here 3 meter, and this is also one short edge discontinuous. This is your interior panel. So that means here you are having how many slabs you have to design? One, this corner slab you have to design, where two adjacent edges are discontinuous. One short edge discontinuous for this purpose. So you can design all of them. That means this one if you design, you can design. That means it is 2 for this one. If you design one of them, you are designing for all of them. So that means if you design only this, so if you design this one, then automatically you are designing, that means this one and this one, all 4 can be. If you design this one, then all of them. If you design this one or this one, it means all of them. If you design this one, then it is 2 for this one. That means 1, 2, 3 and 4. That means you have to design 4 slabs. Out of 9 different conditions, in this particular problem, you are having 4 different boundary conditions, and which you will use the table 26 of IS 456. From using that, you can find out the value of MUX and MUI, calculating alpha x and alpha y for support as well as for span. You can find out that value and just simply follow that that example which I have shown you yesterday, and you can find out that reinforcement. So if you can find out the main reinforcement, later on other reinforcement, actually I am not going to detail of that, other reinforcement you can find out that how much percentage you have to give, that you can find out from that particular clauses which I have shown you yesterday. So this is the one, that building. Now out of that particular one here, one way I can do, what I can do? One way I can do that one, that obviously this is end one, This is one type of frame, and there is another one intermediate frame. That means this frame to this frame all of similar type, whereas this frame and this frame another type. What I can do, I can take to make my life simple, I can just simply design any one of them, either these or this, and then I shall solve the problem, and then I shall go ahead implement that one say construction with that. That way it is not economic, because this frame definitely it will have say it require less actually strength compared to this one, because I am taking the half of the load here. That means say half of this load will come here, half of this will, but this frame having half of this one will come here, half of this will come. So that means this B to H, B, C, D, E, F, G, H, yes, that is true actually here, that is also true, but we are mainly considering that one, that is in the, there is one information, we can use modified external shear walls to control earthquake vibration in multi-story frame. This is your another control mechanism, but that one we can consider this one as a in the design level. What I mean to say, there is one aspect that one you are doing at the design level. Design level means you have designed it and then constructed. So, and there you are having so many different kinds of actually you are having that frame structures, because that one we are only considering for this small course, that only multi-story frame structures. We are not going to shear. There are so many variations of actually, if you go for high-rise structures, you will find out many types of actually your forms. They call it a tubular one, that separately shear wall, other things, all those things are there, and that itself actually another different kind of forms actually you can use it. And also you can plan it properly, that irregular structures, or you can consider just to, okay, fine. So just to give you idea that what will be the this type of structure. So it is possible like this also, that this type of structure, irregular structures, or if we consider that one particular one say frame, then there is a possibility of that. If I consider this one, then you say there is a consider called mass irregularity, then stiffness irregularity. So different kind of things are there that you can find out. And there are after earthquake at well surface and surroundings. I could not get you that well means which one you are talking well, because we consider that well also, that another way also we consider that one as a structure also we consider. Or are you talking that well means water well? That please explain, confirm. And can we use this code for design of high-rise buildings height more than 500 meter? Okay, this is a very interesting question that particular one here, that how far can we go, that how far we are considering this particular frame. That mainly we are talking this one, that I have taken this particular course as a foundation course, and that's why I have considered this one as a actually your limited to only multi-story frame structures. There is another course actually which I have taught actually earlier for so many years, that is called actually high-rise structures. Now whenever you are coming to that high-rise structures, so if we consider that one your say high-rise structures, there you are having different kind of actually forms, and then obviously that 500 meters, say for example Burj Dubai, and there are say for example Empire State Building, which was quite some time that was the tallest building. You can imagine that one, say just to for historical reason I am telling you, say pyramid, that one for more than say 2000 years actually, that you can consider that was actually as a tallest structures in the world. Afterwards say Empire State Building, like there so many buildings came up, you can find out so many, and also that Burj Dubai, and another building is coming up actually there. So now the thing is that this type of structures, what you have to do, it is just simple linear thing will not work. That means just simply you consider multi-story frame or something kind of software, you will popular software, you will use it, not like that. You have to go for that so many things you have to do it actually. Sometimes it happens actually, it takes a lot of time in planning. That means it's not the one that only one group they will do it. They will come up with different kind of solution of different consultants, say maybe 3 or 4 consultants may be invited and come up with certain solution, what type of actually forms you will use it. And on the basis of, because those structures always find out, those structures are always special, and that is an iconic also. And whenever you are talking that iconic structure, so it requires special care. So simple just only say a multi-story frame, that is not possible. So there are certain kind of limitation, other things. Just for your information, I'd like to give you one example. Just let us consider this very simple one. What I can show, let us consider a certain area. Let us consider 5 meter by 5 meter, and I am allowed 4 columns. Now let us say, question is how far I can go up, how many floors I can make it. I have given you 5 meter by 5 meter, not more than that. So obviously I cannot go to for say 100 story. I can go for 100 story building, I cannot go. What I shall do it here, that means if I go, then it will keep on increasing the column dimension. We shall keep on increasing the column dimension. If I do it, keep on, then what will find, then you will not find out that one, that it is coming more and more, that 5 meter by meter. Obviously if I have 5 meter by 5 meter, then I cannot go say here 10 meter from this side, 10 meter this side. I can only go up to 2.5, maximum I can go 3 meter. So that means if this is the land, say 5 meter, that is the one area. So if I go say 3 here and this side 3, so that means maximum I can go 11 meter. So that means with these frame structures, with this small area, I cannot go up to certain level, say for example maximum I can go, say if you really interested, say 3 meter, that way it is feasible. So 3 story, that way it is feasible. So here actually it comes that problem. So that's why whenever you are talking say 500 meter, then obviously you have to consider that only you have told height. What about the footprint? That is also equally important. On the basis of that also you have to find out that whether how far, how many stories I can go. Now let us come back here, this problem quickly. Let us come to this problem. So we are having this one here, this plan, and we are considering one of them, one of the frame we are considering, and that one, let us say I have considered here the C1, C2, C3, C4. That means that the frame at location C frame we are considering. So if I look this frame from this side, then I am getting the C1, C2, C3 and C4. So let us consider 600, 4000. Generally the 600 millimeter means actually your plinth level from the ground. For generally in the ground floor, generally we give little more. You can give 3500 also, that particular one. G plus 3 story RCC frame at C. Now there are certain basic data. Design, because this is the one that certain basic thing actually you have to know, that you have to find out. So design shall conform to the following Indian standard codes. IS 875 for load combination, what type of load you are considering, that is important here. Say for example you are considering residential building, what will be the load? If we consider a classroom, what will be the load? If we consider library, what will be the load? If we consider say I am talking say live load or imposed load. If we consider say assembly building, what will be the load? So different cases you will have. Then you are having say staircase, how much load shall we consider? If it is a balcony, how much load shall we consider? So obviously it all depends that of different kind of utility. Let us consider say balcony. If we really consider balcony, then in balcony we consider say 4 kilonewton per square meter load. But if it is crowded, say for example you are having a building in a balcony, and there is something going on, jumping over that, all those things you are doing, and that one if you consider, so that is overcrowded. The balcony may be sometimes overcrowded. So obviously for that case you have to consider, if it is a normal situation, which also 4 kilonewton per square millimeter coming out, obviously so many people are coming out at a time. If it is say your lecture hall complex where you are having a staircase, when you are going, the students they are going a thin space, but when they are after the class, you will find out the all the people are just jumping and coming out of the class and using the staircase. So considering that aspect, then we consider 5 kilonewton per square meter. So those things are available in IS 875. Then similarly for concrete, how much unit weight I shall consider. If you consider that say what is called say your floor finish, how much shall we consider? So those things you will get it here. Then we are having IS 456, IS 1893. If you would like to more specific, then you should give the year also, that which particular code you are following, that 875 IS 456 because 1978, 1893, long back 1980s you are having one, now recently 2002 you are having. So which one you are following, that also to be mentioned. Concrete shall be of grade M25, steel shall be of grade Fe415, plinth level is to 600 millimeter above ground level. The external brickwork shall be 250 millimeter thickness and the internal walls shall be 125 millimeter. The width of stairs shall be 1250 millimeter minimum. The earthquake zone shall be considered as zone 3. The live load on floor 3 kilonewton per square meter, live load on corridor, and live load on corridor and staircase 4 kilonewton per square meter, and live load on roof 2 kilonewton per square meter. Though I have not considered all those things, the calculation to, but these are the things generally we consider. Depth of foundation shall be at least 1200 millimeter below ground level, and the safe bearing capacity of soil shall be taken as 150 kilonewton per square meter. So this is the one that information required for our calculation. So this is, you can consider this one as a basic data, or we call it actually design basis. That is also you can consider, that is the starting point. Now let us assume something, because as I have told you that I have to calculate the load, but if I do not know that what is the thickness of the slab, I shall not be able to calculate. So as I have told you that one, that whether how shall we get it? So you have to assume certain data. So thickness of slab 125 millimeter, thickness of floor finish 30 millimeter, thickness of ceiling cluster say 6 millimeter, unit weight of concrete 25 kilonewton per meter cube, unit weight of floor finish 24 kilonewton per meter cube, unit weight of plastering 24 kilonewton per meter cube. The dimension of external columns 300 mm into 500 mm, dimension of internal columns 300 mm into 400 mm. What is that? Let me just explain. Let me go back that. So this is external columns, and this one another external column. So these columns you are having certain, and this is internal. So we are having two different dimensions. Dimension of beams in rooms 300 mm, 450 mm. Dimension of beams in corridors, it may be different, but though I have considered same, but it may be different there. 300 mm into 450 mm. Dimension of cross beams 300 mm into 50. What is cross beams? Okay, let us go back to that. So this is your cross beam. So whenever you are talking a frame, I am talking this frame. So that means you are considering this beam, this beam, this. That means here the span is less, so this one can be less also. So this is one, this is another one, this is another one. But this is called cross beam. Now how shall I design the cross beam? Just to give you information, the design of cross beam, you can take actually just simply you can take this one particular floor, you can take it, find out the your say self weight of the wall, that wall you can consider, and then you can use table 12 and table 13 of IS 456. That you just remember that yesterday I have told you that you would say bending moment coefficient and shear force coefficient. So using that you can find out bending moment and shear force. You can find out the bending moment here, you can find out bending moment here, you can find bending moment here like this, and and shear force also here, this side also, left side as well as right side, like that you can calculate. On the basis of that, when you have got that shear force and bending moment, so immediately you can calculate that. You can find out that, you can design the section, you can find out the reinforcement that way. This is called cross-beam that way also. When you are doing this analysis by say a two-dimensional one, that way you can do it. So this is the one I have told you, that cross-beam, that which I have already told. Now dead load. So like this one, there is no other alternative. You have to do this one 120 mm thickness slab. So you can find out. I'm sorry, this one will be square meter. I shall send the new. This will be in square meter. I find out this one will be in square meter. Please excuse me. I missed this one actually here, the square meter. So which is noted down here. So dead load of slab, floor finish. So that means you have to calculate that one for slab. You have to calculate for floor finish, you have to calculate for ceiling plaster, and then you have to add, which is coming 3.989 kilonewton per square meter. So it means that I am getting here almost 4 kilonewton per square meter. Please note, in engineering that you should always offhand you should remember certain values. That means without doing any calculation, if I take 4 kilonewton per square meter, that is good enough. And then dead load due to brick wall of thickness 250, so 15.25 kilonewton per meter, and this one I am getting that 7.625 kilonewton per meter, this particular one we are getting. Now there is one issue, what is that? This is actually, you have taken this one as a solid, but actually that one actually certain kind of voids, that means window is there, maybe door may be there, like that. So then it will be further reduced, because what I am trying to say that this particular example we have given you just to get an idea, because more detail, more tuning, economize, all those things you can do it if you know that what procedure to be followed. So that way you can consider, but here no need of reduction, but if you want to reduce it, maybe 80%, maybe 60% reduction. So that means 6 into 15, so it will be 9. So that means for external wall for 250, I can take this load as say maybe 10 kilonewton per meter or 12 kilonewton per meter, like that I can consider. And similarly this one I can consider say 7.5 kilonewton per meter, that also I can consider. So like that, what I mean to say that this calculation everything fine, offhand that you should have that feelings, that means due to dead load, the load comes here near about 4 kilonewton per square meter. That is the one you can consider, and this one you can consider here. Now UDL per meter length of beam due to slab, floor finish and ceiling plaster, like that. So you can get that particular one here. UDL per meter length of beam due to self weight of beam, which is coming as 2.438 kilonewton per meter. So I am getting here this particular one, I am getting here 2.438 kilonewton per meter. So this is 15.956. That particular one you are getting here, you are getting 2.438 kilonewton. That means if somebody takes say 3 kilonewton per meter, that for the self weight, and that is the one engineering judgment you are considering. That means always you need not go to the detailed calculation of things, but at least once you have to do your calculations so that you can get an idea where from you are getting what is the contribution of load. So that means here you are getting 15.956 kilonewton per meter, that load you are getting from the slab, floor finish, ceiling plaster, and this one you are getting 2.438. That means one can take 3 kilonewton per meter, this one can take 16 kilonewton per meter. If he goes further, he can go up to 20 kilonewton per meter. That is the one I am trying to say, that you think in that manner, that how much load you will, because the thing is that whenever you are doing calculation, most of the cases I have found the students simply they simply use their calculator and find out whether the results they have got correct or not, that they do not understand or they do not get time to understand. So the main thing, whenever you are doing calculation, immediately you should know, okay, these values should not come more than that, these values should come within this range. That idea you should develop. Now live load. So length of each bay 4 meter, that means The each bay, what do we mean by each bay? This is each bay. So this is one, this is one. The spacing between two frames, that is the one we are getting, that particular one we are getting here. So length of each bay 4 meter, UDL per meter, say 12 kilometer per meter. So that means in dead load you are getting something say 16 kilometer per meter, and here on the room you are getting 12 kilometer meter, while in the corridor you are getting 16 kilometer meter. What does it mean? Our objective, the frame or the building you are constructing, that is to take care this much of load, but to construct this one for this live load you require another one, that is almost say 16 kilometer per meter. So that means here it is coming 4:3 ratio. You can find out that one you are getting say 4:3 ratio. That means 1:0.75, or if 1 is the live load, then 1.33 is the corresponding load you require. So that means that way you can find out that how much load you require actually for dead load and how much load you require for the live load. So that particular ratio you have to find out. That means economic mean actually here that if dead load is less compared to the live load, then obviously that is economic, but that is not always true. The dead load becomes more compared to the live load. So on the basis of that you have to find out the ratio and you have to check whether how far actually you have achieved. Now you are having say floor weight. I have considered all of them. I have considered dead load and live load, roof, third floor, second floor, like that I have considered. And then both dead load and live load of roof will be different from other floors, because I have told you. But here for the time being, that's taken. I have considered that for simply same load is considered here. So I have taken the same load, but actually speaking, this load and this one will be different for the roof. That is for the actual case. If you do that one, whatever the problem I have in the beginning, check it and recalculate. So weight of roof the same, third floor also, second floor also, first floor also. So all of them having the same load, I am getting it here. And with the same problem, the problem which we have done earlier. So we are considering earthquake zone 3. For 3 it is 0.16 from the table. Importance factor 1, mobilization factor 5 I have considered. So that means your value will be less. If it is 3, then that means here the same problem, if you really saw that you can do it for 2, you can do it for 3, 4, 5, 6. Impact factor 1, 1.5. Memorization factor 3, 4, 5 say. Then your thing is that we are having that other case. Just to give you idea, I can consider here 4 zones. I can consider this one as 4 zones. Then 2 importance factor, 3 resisting factor, 3 soil condition. So 4, 2 into 3 into 3. So 72 cases. That means for a particular building, you can have 72 cases, 72 different type of cases. 4 zones, 2, 3, 4, 5. 2 importance factor, 1 and 1.5. Resisting factor 3 or 4 or 5, then in 3 cases. Soil condition, soft, medium, hard, 3 cases. So if we consider all of them, so I am getting 72 such cases. That means I can have the 72 actually different kind of solution that we can have for a particular building. That means if you do a particular building, that one, then what happen actually in anywhere in the in India, you can actually provide that way, because that one we are having only 72 cases. So zone 3 it's 15 meter D. So then I am getting here 0.377 is for that. We are getting here 2.5 earthquake coefficient 0.04, VB equal to 77.338 kilonewton. And if you make it here, then label, then I can find out the roof, third floor, second floor, first floor. and I am getting this value. So I can get this value here. This is the one, the force, that lateral force that we have to apply. So this is your, then we are getting here earthquake load that we can find out, and that we have to apply. Now we require load combination. So we have taken, there are many more combinations they use it, but these combinations are sufficient. So that means dead load factor only 1, that means one case number 1 dead load only, 2 live load only, 3 earthquake load. That means these 1, 2 and 3, if we can use it, then I can derive other load cases. So 4 means I shall take from this case this much of factor and this one, and then I can get the new in u. Fifth one 1.2, 1.2, 1.2. Sixth one 1.12 plus minus, so I am taking minus 1.2. 7 1.5 and 1.5, there is no live load. 8 1.5 and minus 1.5, 9.9 and 1.5, 10.9 and minus 1.5. So this particular one we shall consider the load. That means if I can solve for 1, 2, 3, remaining other I can find out on the basis of that USA calculation. Now I am going for analysis model that we are going, and then 3 load cases only, that we shall, first 3 load cases we shall consider. So what I have done, I have given the node number. So 1, 2, 3, 4, 5, 6. 6 means actually the middle, 7, 8, 9, 10, 11, like that. We are having total 32. We have total 32 nodes, and then what we shall do is actually we shall find out, and your, what about the member number? Member number, say first element, second element, third, fourth, fifth, sixth, seventh, eighth, 9th, 10th, 11th, 12th, 13, 14, 15, 16. So first 16 columns. Then here I have 2 elements, 17, 18, 19, 20, 21, 20. Why I require? Because so that I can get at the middle, I can get immediately bending moment in shear force. So like that I am having here 2 plus 2 plus 2, 6, 1, 2, 3, 4, so 24. That means there are 16 columns and 24 beams. So total 40 elements. So I have 32 nodes and 40 elements. And then I have applied the load at the 5, 12, 19 and 26, the lateral load I have applied there, and vertical load I have applied here. So if you do that one here, first thing that you find out the coordinates 1, 2, 3, 4, that 0, then 5, 6, 7, 5, 6, 7, 8, 9, 10, 11, 4.6, then 12, all those things, just to give you one. So this is one, all 0 y, this is all of them having the same y, this one having same y, this one having same y, this one having same y. So like that we have given all the nodes. Then load at 5, 12, 19, 26. So 5, 12, 19 and 26. This way I am giving the load. And this is the case number 3, because I am having that one, they've got that other loads we are having different. So case number 3, that load I am giving in the x direction, the load we are giving it here. Then we have analyzed the structures, and then we have calculated the nodal displacement. 1, 2, 3, 4 operator fixed, so this is 0. Then 5, 6, 7, 8, that all those things are given, and then you can find out that one, say we can find out this is a negative, means downward. Negative means downward, the displacement we are getting it here. So then 9, 10, 11, 12, 13, 14, 15, 16, then 17, 18, 19, 20, 21, 20. So I have given that displacement also for each case, 1, 2, 3. So like that you can find out the displacement, other things actually you can find out. This is the way actually, because just to give you idea that for all of them, only in the commercial software you find out that one they have given in a different manner. But generally it will be more than sufficient to know, and rest of the things you can actually derive, because if you have that information. Now element data, for element data that I have given in the different tables. So 1, 2, 3, 4, 5, 6, 7, 8, like that. So I and j, first node and second node I can give, and on the basis of that you can find out. This is also another 9 to 16 actually they are given. Then 17 to 28 that is given. So area and IZ and E. So the 29 to 40 again I can give that value. So if you give that one with this with data, then you will get that one your say result. And in this case, you are having only since it is two dimensional, that's why you are having Fx, Fy and Mz, that bending moment. So axial force, shear, and you have that bending moment. So I can get that particular one here. That means this one is nothing but the vertical force. And just to give you idea, just so what we are doing basically here, so 1, 2, 3 and 4. So we can find out this one. So you can find out this one. This is your say element number 1, 5, 9, 13. So these are the elements from where you will get the value of this particular one. We will get it, this one. And please note, whenever we get that one, say your value, that one will be in the local direction. That means here for this case I am considering this is my x, this is my y. So this is axial force. So that is the one actually we do it and we find out that. This one, whenever we find out, just one more important thing I would like to show you. This is the one that different element we are getting these values. So now just to give you idea of this one. This one, how much it is that to give you? So 5, 6, 7, 8, 9, 10 and 11. So I am getting this particular one 5, 6, 7, 8, 9 and this is your, what is the element number? 17, 18, because I have actually 4 columns in each. So 4 into 4, 16 columns. So 17th element, that one you are having the element. So 17, 18, then you are having 19, 20 like that. So I have to find out this one, how that bending moment actually, what is the bending moment? For this case, if we consider this is positive, this is positive, what about this is actually your element, this is 5 and 6 and this side you are having 6 and 7. So this is negative, this particular one here. So if we consider this one negative, this is also negative. So that means for this element, if it is positive, that means this side, and if it is negative, positive this side, that means it is in the below. That means here the bending moment should come like this. Then only this one is coming positive, this one, that one say positive that way. So let us see how much it is coming there. I am considering this one say 1, and where I am getting this one say positive here, this is positive, that means whatever I have told, that is correct. So like that for case 1, case 2, like that actually I found out, and from there you can get the bending moment and see. So like that, then I have told you the support reaction, whatever the value we are getting it here for support reaction for 3 cases, and that way we can find out. So there just simply I have given one example for that case I have considered, and this is the one support reaction which will help you to do the column design. From there you can find out the load. You can take different combination out of it, and you can find out which one is coming actually maximum. From beam design, I am not going to detail up all those things, because the same thing I have considered this one for the 1.5 times the load that I have got it here, and on the basis of that, whatever we have done it yesterday, same thing just I have demonstrated. This is the thing I have given you. So just I have given you this one as an example taken for demonstration. More detailed analysis can be carried out considering different roof load. If you, as I have told you, pointed out, load of transverse walls is not considered, that also should be considered there. It will add more load, only thing that value will be changed in calculating lateral load due to earthquake. It is possible to solve the problem using commercial software. Here an attempt is made to show the calculation at different stages. And one thing, this document is prepared by programming in Python. So I have not done it any manually, because this whole document I have prepared by using that Python language, and this way it has come. So that means if I change the value, they automatically other values can come. That if I use the different zones, automatically those things can come up. So I think that I have gone to this particular one. I should give more detail, but anyway, I thought that it is, since the thing already given, so I hope that you have gone through it. So, and this one you try to use it in a commercial software, you use it, and then you can find out that. But the basic idea is that I have tried to mention here in this particular in this session, that how generally we solve the problem, because nowadays the commercial software looks like that you would say black box, but that is not the thing. There are so many things that they are involved, and we go step by step all those things. Thank you very much. Thank you all.